This is section 4.2, recursive definitions. Let's take a look at a very famous recursively defined function or a recursive definition, which is the set of Fibonacci numbers. So if you'll recall, to find the next value of a sequence in the Fibonacci numbers, I'm going to take the sum of the two values before it. So 1 plus 1 equals 2. And then 1 plus 2 equals 3. And then 2 plus 3 equals 5. And 3 plus 5 equals 8. And we can see this pattern continuing and continuing, and it makes it very easy for us to find the next Fibonacci number in the sequence. Now what we want to do is take a look at how we can write that mathematically using a recursive definition. So let's take a look at how we might write this. F sub 0 means that it's a starting point. So even though you don't see a 0 here, and that's okay, we're not saying the first number in the sequence is a 0. We're saying let's start the function at the value of 0. Now the reason that we have to do this is because to find this number 1, I need to take 0 plus 1. So what I'm doing is I'm defining f of 0 as 0, and I also have to define, let's use a different color there, f of 1 to be 1. Now why do I have to do that? Because in order for me to find my next number, I have to know the two numbers before it. So notice I'm defining that this is my first starting number, this is my second starting number, and then any other thing that I want to find, f of n, can be found by taking one value before it plus two values before it. So for instance, to find f of 2, which we already know here is 1, I'm going to take f of 1 plus f of 0. Well, f of 1 was 1, f of 0 was 0, so that term is 1. If I want to find f of 3, my recursive definition tells me to take f of 2 plus f of 1. f of 2 I just found was 1. f of 1 was already defined here as 1, so that value is 2. And if you'll notice, this is f of 1, f of 2, f of 3, so it's working. f of 4 would be f of 3 plus f of 2. f of 3 was 2. f of 2 is 1. That gives me 3. Does that match what I have? Yes, it does. And we can see that that pattern would continue and continue. So what we know about recursive definitions is that we cannot find f of n without knowing, in this case, the previous two terms. Now sometimes it's going to be one term, sometimes it will be three terms that you will need to know. That is called a recursive definition. So there is a way sometimes to explicitly define a function, but quite often it is difficult to figure out. And so an explicit definition would not require us to know anything else about the function at all. So we'll take a look at that one in a minute. So again, let's say I have a sequence a sub n, we already know that's the notation that we use for a sequence, of the powers of 2. So this is an explicit way to write what the next value in my sequence would be. So this would tell me that a sub 0 is 2, that doesn't look like an a sub 0 is 2 to the 0, and anything with the 0 power is 1. And then a sub 1 would be 2 to the first, and 2 to the first is 2. And a to the 2 would be 2 squared, 2 squared, which is 4. And a sub 3, which of course just means the third value in the sequence, is 2 to the third, why do I keep writing a? 2 to the third, which is 8. And we could continue this pattern over and over and over again. What we want to do is think about how could we take this and also write it recursively. So obviously I have the answer for you already, but let's take a look at the process that we would go through. We know that we must start with a starting point. So I'm going to start with my very first value. And how did I know that was the first value? Because here it said n starts at 0. So my very first value had to be a sub 0, or 2 to the 0, which was 1. So that's where I got this from. And then I needed to say, to get from here to here, what did I do? And then make sure that pattern holds as I continue down my list. So to get from 1 to 2, it looks like I multiplied by 2. To get from 2 to 4, it looks like I multiplied by 2. To get from 4 to 8, it looks like I multiplied by 2. So what I'm saying is, I took the value before and multiplied it by 2. So how do I write that? I say to find the next value in the sequence, I'm going to take 2 times the previous value. And of course I could have written this as an equals 2 times an minus 1, which is really saying the exact same thing. That to find the next value in the sequence, I'm taking the value before it and I'm multiplying by 2. Now, hopefully you've made the connection here that this is very similar to induction that we just talked about. A basis step and an inductive step. Except that right now this is not going to be an inductive step. So let's take a look at how we talk about these. When we set up a recursive definition, we must have two parts, just as we had talked about before. One is the basis step, which essentially tells us the starting point. Just like it did when we were doing inductive reasoning, we're basically saying this is the starting point. This is the first value, or the first two values, or the first three values, etc. The recursive step, kind of like the inductive step, says where to go from there. So give a rule for finding its value at an integer from its values at smaller integers. So this is our direction. Oops. The direction we will go. So again, it's called a recursive definition or inductive definition. We're mostly going to call it a recursive definition. So let's take a look at an example. Now this one I wasn't very clear in my instructions, but basically what I've done is I've given you a recursively defined function. This is the basis step, which is basically saying you're starting at the number 3. The recursive step is saying here's where to go from there. To find every other number, you're going to take 2 times the number before it and add 3. So I already know that f of 0 is 3, and they're saying find f of 0 plus 1, which is 1. So how do I find f of 1? Well, I take 2 times f of 0 plus 3, or 2 times 3 plus 3. That's 6 plus 3, which is 9. Then I want to find f of 1 plus 1, or f of 2. Well, f of 2 says take 2 times f of 1 and add 3. So f of 1 was 9, because I just found that in the step before. So 2 times 9 plus 3, 18 plus 3, which is 21. So we get the idea that all we're doing is applying the recursive step over and over and over until we find however many values they ask us to find. So in this case, perhaps they ask us to find the first 4 terms in the sequence, and that is what we did here. Here's a question I would like you to try on your own. So I'm asking you to define the factorial function, and of course factorial is n factorial, meaning take whatever n is, which is going to be an integer, times every other integer below it all the way down to 1. So if you're stuck on how to do this, I suggest making yourself a list. Start with f of 1, f of 2, f of 3, etc. And then define your function by giving me the basis and recursive steps. When you're ready, press play to see how you did. So again, we would start this by saying, let's build a list. if I took, say, even starting at f of 0, f of 0 is 0 factorial, and hopefully we all know 0 factorial is 1. F of 1 is 1 factorial. 1 factorial is 1. F of 2 is 2 factorial, which means 2 times 1, which is 2. F of 3 is 3 factorial, which means 3 times 2 times 1, which is 6. F of 4, 4 factorial, is 4 times 3 times 2 times 1, which is 24. And so essentially what I'm looking at is how can I build a pattern? Well, it looks to me like the 2 times 1 is the same, and all I did here was take it times 3, which happens to be n. And then I say that it looks like 3 times 2 times 1 is the same, and all I did here was then take it times 4, which happens to be n. So how could I define this? I would say my very first value, because I need a starting point, f of 0 is going to be 1. Then to find each other one, I'm taking whatever I had before, which is the 2 times 1 or 2, or the 3 times 2 times 1 or 6, and I'm taking it times n plus 1. So to find the next value, so this would be f of 3 plus 1, says to take 4 times f of 3. Now, does that hold true? Well, this would be 4 times what was f of 3? 6, which is 24. So my recursive definition works. So notice I can compare this and actually plug them into my recursive definition and make sure that I've done this correctly. I want to also take a look at not just a recursively defined function, but a recursive definition of a set. And the reason I want to look at that is because I also want to look at how we will use proof by induction. So if we want to recursively define a set, just like when we recursively defined our function a few moments ago, we need to provide two things, which is the initial set of elements, which of course is the basis step, and then we need to have the recursive step, which says from where we started, where are we going? So it's kind of a roadmap. Here's where you start, here's where you're going. So for example, let S, and again S is a set of values, be recursively defined by the fact that my basis is that I'm telling you that 3 belongs in the set. 3 is an element of S. My recursive step says x plus y is also an element of S if x belongs to S and y belongs to S. So let's take a look at what that definition is saying before we try to prove this by induction. If I were to then build, and again, you might be wondering where this came from. Whoops, let's maybe not cross through it. I'm going to explain how I know that this tells me that it's the set of all positive integers divisible by 3. So essentially what this is saying is I'm starting with the number 3. Then I'm saying to find another value, so 1 was the basis step, that 3 belongs to S. 2 is saying if x belongs to S, so the only number I know right now belongs to S is 3, and y belongs to S, then their sum belongs to S. So 6 must belong to S. Then I'm going to apply it again. Well, my only numbers to choose from are 3 and 6, so I'm going to say 3 plus 6, which is 9, also belongs to S. And if I take 9 plus 3, again taking any two numbers that belong in the set, that gives me 12. So you might be saying, well, why didn't you take 6 plus 9? Well, I sure could have. 6 plus 9 is 15, which would be the same as me taking 3 plus 12, which is 15. So 15's in the set, and you can see the pattern that I've created here is that I basically have the multiples of 3. So S is the set of positive integers divisible by 3. So we're going to use this information now to create a proof by induction, and we define our least element, which is 3, and then give a definition that allows us to find the next elements given that first element. So I've shown you in a non-proofy way that the set S is the set of integers divisible by 3. What I'm trying to do now is show you the mathy way, which is basically saying we're going to let A be a set of all positive integers divisible by 3. And I want to show that A is equal to S. So S being what I already recursively defined as my first value is 3, and each other value has to be created by other values that are in the set. In order to show, and hopefully you remember this from discrete mathematics, in order to show that two sets are equal, we have to show that each set is a subset of the other, and therefore they must be equal sets. So we'll start, and it doesn't matter which one you do first, but we'll start with this one. Let's prove that A is a subset of S, which means every element in A belongs to S. So we must show that every positive integer divisible by 3, because that's what A is in our set S. Okay? We're going to use induction to show this. So remember, induction starts with a basis step, and the basis step says that the very first value in the set is true. So we're going to let our statement, P of n, be the statement that 3n belongs to S, which is just a fancy way of saying that all of our numbers are divisible by 3. The basis step is the very first element, P1, which is true because P1 would be saying 3 times 1, which is 3, belongs to S. Well, do we already know 3 belongs to S? We sure do, because that was our basis in our recursive definition. Our inductive step is to show that if Pn is true, and remember, Pn doesn't have to be 3, it can be any Pn, then we know that Pn plus 1 is true. So how do we show that? Well, we assume that Pn is true, and Pn says 3n belongs to S. So that's what I'm saying here. 3n belongs to S, which I could say 3n belongs to S. Since 3n is in S and 3 is in S, which I just proved right here, it follows from the recursive definition of S. Remember, the recursive definition says x plus y belongs to S if x belongs to S and y belongs to S. So I'm using this definition here. It follows from that definition that 3n, which is in S, and 3, which is in S, would give me 3 times the quantity n plus 1, and that would also be in S. So therefore I have proved the first part. A, which is the set of all positive integers divisible by 3, is a subset of S. Alright, now I have to go the opposite direction. I have to show that S is a subset of A. Remember, S is the set that I came up with. A is the set of all numbers divisible by 3. Integers divisible by 3. So all initial elements of S are in A. So I have to show the basis step that the initial element of S is in A. So the initial element of S is 3. Does 3 belong to A? Yes, because A is the set of all integers divisible by 3, and 3 is definitely divisible by 3. The inductive step, so now I'm choosing the inductive step of my recursively defined set. X plus y is in A. So I'm saying x plus y is in A whenever x and y are in S. So x plus y are in S. So how do I prove that? Well, if x and y are both in A, then it follows that 3 divides x, which basically means x is divisible by 3, and 3 divides y, which means y is divisible by 3. And from that, we can say that 3 would also then divide the sum of those two values. So what have I shown? That S is a subset of A. So my overall conclusion, since I have shown that A is a subset of S, and S is a subset of A, therefore A and S must be equal sets. So let's go back to our Fibonacci numbers, because this is one that you're going to see so often whenever we're dealing with recursive definitions and of course with inductive reasoning or inductive proof. So if we go back to the Fibonacci numbers, we know how that we define them recursively. We defined the first two values and we said essentially take the two values before it and that gives you the next value. And what I want to do is I want to prove this statement, that whenever n is greater than or equal to 3, that f of n, or f sub n, which is basically saying that number in the series, so starting with 3, would be greater than alpha to the n minus 2. And then they give me a value for alpha, 1 plus radical 5 divided by 2. So if I'm going to define that, or if I'm going to prove this using inductive reasoning, you know that I first have to start with the basis step, and the basis step in this case would have to be that I'm finding both f of 3 is greater than alpha to the first and f of 4 is greater than alpha squared. So that is what I've done down here. So I'm saying alpha is 1 plus radical 5, and that value is less than 2. So essentially I've proved that f of 3 is greater than alpha to the first, because f of 3 is the value of 2. And again, how do I know that? Because my numbers were 1, 2, 3, 5, 8. So I'm saying 2 is greater than alpha to the first. True. Then I'm going to do the same thing. I want to prove f of 4. Remember, f of 4 is 3. Is 3 greater than alpha squared? Well, alpha squared is this guy, which really turns into this guy, and 3 is greater than that. So check, check, I've proved my basis step. And now comes the fun part, and as you can see I have it all laid out for you so you don't have to wait for me to uncover it. But let's look at where we're starting and where we're going before we start going through all of this business that we're going to go through. Essentially what we're saying is we have to assume that this is true. This is our inductive hypothesis. We're going to assume that f sub j is greater than alpha to the j minus 2, where of course alpha is still 1 plus radical 5 over 2. Now, what we then need to show is we need to prove that p of k plus 1 is true, which again, using my inductive hypothesis, means that f to the k plus 1 is greater than alpha to the k plus 1 minus 2. Well, of course, that means that essentially I'm saying that it's greater than alpha to the k minus 1. So this is where we want to end, and this we're going to use obviously as a true statement. So where am I going to start? Well, since I'm trying to prove Fibonacci, let's start with my recursive definition that says to find f sub k plus 1, I'm going to take essentially the two values before it. True. I know that to be true. Then I'm going to use my inductive hypothesis, which says f of k is greater than alpha to the k minus 2. Also, f of k minus 1 is greater then alpha to the k minus 1 minus 2, which of course is known as k minus 3. So essentially I can do that. It's legal because we're dealing with an inequality. So I know that this side of my equation will certainly be greater than this side of the equation based on the fact that I'm assuming the inductive hypothesis is true. Now from here, it's pretty straightforward. So getting started is really the hardest part. From here, I'm really just doing math, just doing algebra. Let's distribute or factor out the alpha to the k minus 3 out of both of those terms. Let's then substitute the value for alpha back to my function and then simplify it. And then, hey, if you remember on the last page, when I found f of 4, that was alpha squared. It was 3 plus radical 5 over 2. So I just did a substitution. And then I know alpha to the k minus 3 times alpha squared. I can add those exponents together to get alpha to the k minus 1. And therefore, again, adding this left side, I can say that, and again I'm just doing a substitution, that f of k plus f of k minus 1 is equal to f of k plus 1. Notice what I've ended up with, which is exactly what I wanted to end up with. Now, I know I didn't go through a ton of examples in this video. I'm assuming that you've also taken discrete mathematics with me here at Bellevue University. So if you need some more examples of some great recursive definition and inductive hypothesis and definition practice, go to my YouTube page, look for discrete math recursive definitions, and you will find another great video with different examples.